Let's go over to 2008 AP multiple choice non-calculator section. So the first one, limit as x approaches infinity. If you remember how to do limit at infinity, it's all about like horizontal asymptotes. So top bigger than bottom, bottom bigger than top, bottom equal to top. This one is 0. This one is the ratio. This one is infinity or does not exist depending on, or negative infinity depending on which we have. So look at this one. They're trying to trick you. Let's just multiply the x's together. We get negative 2x squared. Multiply the x's together here, you get x squared. So it's a ratio, which is negative 2. So B. This one, they don't integrate 1 over x squared. Remember, that is not natural log. Don't let them fix you. The only time it's natural log is when there's no power on the bottom, when it's a linear on the bottom. Anytime it's linear on the bottom, natural log. In this case, you gotta move it up. So integral of negative x squared. Add 1 to the power, divide by a new power. You get x to negative 1 over negative 1. Also known as negative 1 over x, if you're trying to make it pretty, to match. Which I didn't need to, because they had it the way it was, so it's a D. Overdid it there. Next one, they want to take a derivative. So take a derivative. That is a product rule with a chain rule inside of it. So let's do that. This would be my UV. The derivative of the first one is 1 times the second one left alone. Plus the derivative of the second one. Derivative of that is a chain rule. Bring the 3 down. Do the inside alone. Multiply by derivative of the inside. Don't forget that. This is all the derivative of this guy. Then times the first one left alone. X minus 1. Now, if you notice, my answer doesn't match one of these. I gotta do a little more, so I gotta factor out. You could always factor out this guy, right? They always have the same one of that with the power. So pull that out, this one. X squared plus 2 squared. That's gone. There's only one of these guys left. What's left on the inside is x squared plus 2 plus 3 times 2x times x minus 1. Simplify this a little bit. That's 6x. Distribute. 6x squared minus 6x plus x squared plus 2. Add these up, I get 7x squared minus 6x plus 2 times the thing I pulled out. So that'll be this one, D. 4, we're going to integrate this. These are reverse chain rules. I guess you do use stuff, but it's not worth trouble. So these are reverse chain rules. So remember, reverse chain rule is you integrate the outside. So integral of that would get you integrate the outside, leave the inside alone, times it by 1 over derivative of the inside. So like in this case, that's an integral of sine is negative cosine, leave the 2x alone, times 1 over derivative of 2x. 1 over derivative of 2x is 1/2. Do the same thing with cosine. So plus derivative of cosine is just sine, leave the 2x alone, times 1/2 plus c, which would get me B. Move on, 5. The limit as x approaches 0. Well, first thing I always do is plug in my limit. Anytime it's not infinity, I just plug it in, see what I get. In this case, I get 0 plus 0 over 0 minus 0. So 0 over 0. Two options. I could do L'Hopital's rule if I want. Or in this case, I think it's actually easier if I just factor out. I know they both have an x squared. So you factor out an x squared, and you get this. Or a little nicer. Limit as x approaches 0 of x squared over x squared. 5x squared plus 8 over 3x squared minus 16. These cancel out. Now I can plug in 0 again, see if it works. These are gone. I get 8 over negative 16, negative 1/2. So A. Next one. Let f be a function defined above. Which of the following statements about f are true? F has a limit as x equals 2. So limit, remember, only cares about what's happening, not add 2, but around 2. So I don't care about this guy, I care about this guy. Does that have a limit? So let's see. If I break that up, x squared minus 4 over x minus 2, I could factor the top. X minus 2 over x plus 2 over x minus 2. These cancel out. So really that's just x plus 2 with the hole in it. So I could plug that in and get 4. So yes, it has a limit. Is it continuous? So this is x plus 2. If I plug in 2, I get 4. If I plug in 2 here, I get 1. So it's not continuous. These do not match. Basically, if you plug in this value into both, they're not going to match. This one you get no solution when you first try to plug it in, but then when you simplify it, you actually get 4. So not continuous. The 4 and 1 do not match. Is it differentiable? Well, to be differentiable, we got to be continuous. So it's not. If it's not continuous, it's not differentiable. So it's only A. 7. Particle moves along the x-axis with velocity given by this for time t is greater than 0. If the particle is at position x equals 2 at time 0, what's the position of the particle at t equals 1? So there's kind of two ways to do this one. One way I think you do this, if you integrate velocity, you get the position, but you get plus c. How do you find the c? You plug in your initial point, 2, 0. That's one way to do it. And after you do that, now you can plug in 1. Other way to do that, so what we talked about, if you have velocity and you want to find position, but you don't have the equation for position, what you can do is add the initial value, plus you could integrate the velocity from that initial value to what the point you want, so 3 to 1. So either way is fine. Either way doesn't matter. I think this is actually a little easier if you do the old school way, which I'm going to do in a second. With the integrated velocity from the point's a lot easier if you have a calculator. So with the calculator version, I'm going to do that. But without a calculator, probably do it this way a little easier. So I'm going to integrate velocity. So I'm going to integrate 3t squared plus 6t. And I get 3t cubed over 3 plus 6t squared over 2 plus c. So I'm going into the problem here. My s equals t cubed plus 3t squared plus c. Now I gotta figure out what that c is before I do anything else. So I have my initial point right here. At t equals 0, which is always your x, you get 2. So plug in 0, it equals 2. So c equals 2. So my formula is actually this, t cubed plus 3t squared plus 2. Now that that's my displacement formula, all I gotta do is plug in 1. So plug in 1, s of 1 would equal 1 plus 3 plus 2. So I get 6. After all that, you get 6. So that's the idea. So again, two ways to do it. One way is to integrate velocity from 0 to 1 plus initial value 2. I think that way is a little easier when you do with a calculator. Just do that. By hand, you go, okay, how do I go from velocity to displacement? You integrate. Don't forget you get a plus c. How do you find a plus c? Well, they give you the initial point. Plug the initial point in, and then you can plug in 1. So 8. F of x equals cosine 3x, then find f prime of pi over 9. So we want to take a derivative of cosine. That's a little chain rule. So we're going to take the derivative of that. We're going to get the derivative of cosine is negative sine 3x times 3. Remember, chain rules, you just multiply by derivative on the inside. Now I got to plug in pi over 9. So it's going to be negative sine 3 times pi over 9 times 3. Now, if you notice all the answers, you always have to simplify trig functions in AP Calc. So let's simplify that. Sine is reduce of pi over 3 times 3. Pi over 3 is a 60-degree angle. So rad 3, hypotenuse is 2, 1. Sine is so opposite of hypotenuse. So negative rad 3 over 2 times 3, or negative 3 rad 3 over 2. So E. Next one. The graph of a piecewise linear function f is shown in the figure above. So this is the graph of f. If g of x equals the integral from negative 2 of x of f of t, which is following is the greatest value. So this is like an APFTC question. Right, so here we have the integral from negative 2, which starts right here, to whatever value. That's just the area. That's all this means. So the first one's g of negative 3. So let's plug in, I'm going to do this up here so I have a little space. So negative 2 to negative 3 of f. Well, that's going the wrong direction. Right, it should go low to high, not high to low. So I got to flip it, make it negative 3 to negative 2. So that'll be the area from here to here, like this area right there. That is a positive area, but then I had to flip it, so this is actually be a negative area. So that's probably not going to be the greatest. B, g of negative 2. I'll put that down here. So that'll be the integral from negative 2 to 2 of f of x. Negative 2, sorry, of f of x. Well, those are the same, so it's just 0. So that's 0, so that means a is already gone because a is negative. C, g of 0. So we'll integrate from negative 2 to 0, so it'll be this area right here. Pretty good. G of 1. That'll be from negative 2 to 1. That'll be all this area, so that's even better. So this is out. Right now, that's the leader. G of 2, so it's the area from negative 2 to 2. So from here all the way to there. Now this will be a little lower, right, because this is negative. So it's like, look, the highest one is right here. So this is the highest. This is a little bit less because you're subtracting off this. And since it's multiple choice and this should might work, you just got to say that's the answer. So it's the area from negative 2 to 1. Next one. So I'll have to move up and down for this one. The graph of function f is shown above for 0 to 3. So from 0 to 3. Which has the least value. So I'm looking for the least value. So the integral from negative 1 to 3. So this is the area. So this is the whole thing filled out. That's all of that. So that's what that is. Next one, with the left Riemann sum from 1 to 3 with 4 subintervals. So left Riemann sum. So like that. I have 3 subintervals. It's the same. That doesn't really matter. Left Riemann sum. So we're starting on the left side. So left across, left across, left across. So that to me an over approximation. So this is actually more. So B is bigger than A. So right of these two, B is the bigger one. Right, it goes over. I want the least one. So A right now is the winner. Right Riemann sum. So let me erase this. Let's do a right Riemann sum. So same lines. So now right Riemann sum start on the right hand side and go across. That's an under approximation. So that's the lowest by far. So right now this is a leader in the clubhouse. Midpoint, remember midpoint's always kind of like halfway in between. It's close to the area, but not a little bit above or a little bit below. Trapezoidal also, like these two are better approximations than left and right. So if you're looking for a max or min or greatest or least, it'll be either left or right. And in this case, we're looking for a least, it'll be the right Riemann sum. These other two are close, are better approximations, are closer to the area. So C is the right answer. That's the that has the least value. Next one, the graph of the function f is shown above. Which of the following could be the graph of f prime? So you have all these graphs. I don't have space, so let's draw it. So it's our information all in the same picture, but let's just draw the derivative. This is f. Let's draw f prime. Remember the way you draw f prime, you always want to find the zeros first. So like here, my zero will be right there, and then like right here. Before that zero, remember, so this is the derivative. So we're looking at the slope. Slope here is increasing, not increasing. It's positive. It's going up. Right. This is increasing, so that means over here it should be positive. Over here you're decreasing, or your slope is negative. So it should be on the negative side of this graph. So it'll be kind of like this. And then on this side, you're positive again. On this side, sorry, you're positive again. Your slope is positive. So my derivative is positive. So it'll look kind of like that, kind of like a parabola centered at the y-axis. Looking at these, that's close, but centered not correctly. B is the right answer. So there's that one. 12. If f of e to 2x, then what's f of if f of x equals e to 2 divided by x, then f prime is, well, this is a chain rule. So remember the way you do e's is you copy it times by derivative of the inside. Now let's talk about that. I have 2 over x. What's the derivative of that? Well, I can't take a derivative that way. I got to rewrite it. So 2x to the negative 1. So take a derivative of that means bring it down, subtract 1 off. I get negative 2 to the x to the negative 2. So I get that, which answers that. Now again, notice how they made it nicer. So I see nothing with the negative power, so let's make that a little nicer. Negative 2 x squared over e to the 2 over x. And then which one is that? That looks like D. Right, because you try to match it, and nothing here had a negative power. So I had to rewrite it. We got that. Next one. So another derivative one. If f of x equals this, then find the derivative of f of natural log x. Ooh, that's a little tricky. So first let's take a derivative. So if it's a chain rule with the inside's natural log. So lots of ways to do this, sorry. First we could just rewrite it. Let's actually plug natural log into this and see what we get. We get natural log of x squared plus 2 to the natural log of x. Right, so first thing I do is we'll just figure out what this inside is. So what's f of natural log of x? That's plugging natural log in for all my x's, so I get this. Now I gotta take a derivative. Well, the derivative of this one is a chain rule. Bring the 2 down, subtract 1 off. Times by derivative of the inside. Derivative of the inside, derivative of natural log is 1 over x. Plus the derivative of this one, 2 times natural log x, that's just 2, times the derivative of natural log x, which is 1 over x. So I get, if I look at this, which does that match? I get this. 2 natural log of x over x plus 2 over x, which gets me 2 natural log of x plus 2 over x. A. Next one. The polynomial function f has the selected values of its second derivative given in the table above. Which of the following statements must be true? So they give you the second derivative. So remember what the second derivative tells us? Second derivative tells us concavity and inflection points. But to be an inflection point, you need a sign change. Plus second derivative means 0. So you need the derivative to be 0 undefined and a sign change. The first two talk about local min, increasing, decreasing, and local max. That's all the first derivative, so these are out. So it's between these two. Graph of x has a point of inflection x equals 1. Now that's tempting, right? It does look like it does equal 0, and there's a sign change. But the problem here is I'm not sure what happens in between 1 and 2. It has to be right next to it. Like if I gave you 1.01 and 0.999, then I could go, okay, it's probably a sign change. But here you have no idea. Maybe 0.5 is the inflection point. This is like not an inflection point. So it's hard to tell. So that's why that one's like mostly true, but not totally true. The graph f changes concavity on interval 0 to 2. So from 0 to 2 does it change concavity? That's just a sign change. And it does. From 0 it's 5, from 2 it's -7. So it definitely changes sign. So because this has a less requirements, these are both kind of true or half true. This is actually totally true. The only requirement is you need a sign change. It does change signs. Here you need a sign change like right around 0, which you can't necessarily show. So the answer here is E. So that's a tough one. Like it gets rid of 2 easily, but then those two are, that's a tough one. The next one, they want me to integrate this. This, like it kind of looks like an inverse trig function, but there's an x on top. So this is actually just a u sub. So we're going to let u be the bottom, x squared minus 4. Take a derivative of both sides, du dx equals 2x. Now we want to solve for dx. So multiply both sides by dx. du equals 2x dx. Remember, the whole point is to get dx by itself, so I'm going to divide by 2x. So I get du over 2x equals dx. So now that's my dx equals, so I could sub everything in. So integral, x is still there. My integration sign is disgusting. Instead of dx, it's du 2x. Right, so again, none of this x stays on top, nothing happens to the x. The bottom is now u, and my dx is now 2u over dx. The x's cancel, and you get the integral of 1 over u. Pull out the 1/2, almost forgot about that, du. Integral of 1 over u du is natural log, so I get 1/2 natural log of u plus c. And then sub and plug your u back in, so 1/2 natural log of x squared minus 4 plus c. So what is this one? So there we go. 16. If sine of xy equals x, then dy dx. So this is a separable differential equation thing. Or implicit differentiation, I should say, actually. So if sine of x equals that, then find dy dx. So we got to take a derivative of both sides with respect to x. So take the derivative of both sides. So on this side, the derivative of sine is cosine. Leave the inside alone. Times by derivative of the inside. Now, derivative of the inside is where it sucks, right? That's a product rule. It's x times y, so product rule. Derivative of the first one. Derivative of x is 1. Leave the second one alone. Derivative of the second one. Derivative of y is 1, but it's the wrong variable, right? I'm taking with respect to x, that's a y. So it's going to be 1 dy dx. Then you still have to leave the second one alone, so we're going to leave x alone. On this side, derivative of x is just 1, so it's just 1. Now we distribute, so we get y cosine xy plus x dy dx cosine xy equals 1. Now the whole idea is to get dy dx by itself, so we're going to subtract this from both sides. So I get x dy dx cosine xy equals 1 minus y cosine xy. Then we're going to divide by what's not dy dx. So divide by x, divide by that. So I'm going to divide like this. Dy dx equals 1 minus y cosine xy over x cosine xy. And that would be D. Okay, next one. 17, the graph of function f is shown above. It has horizontal tangents at 2 and 5. So 2 and 5. Let g be the function defined by that. Another APFTC question. For what values of the graph does g have a point of inflection? This is a true APFTC tough question. So g of x equals the integral from 0 to x of f of t. And remember, that means area. Now the question is, I want a point of inflection. Remember, how do you find a point of inflection? It's when the second derivative of g equals 0 or undefined, plus a sign change. Right, so I have g of x. I gotta get always the second derivative of g. So the first derivative of g will be the derivative of this, which is derivative of integral cancels out. You just get f of t. Or f of x, actually, sorry. And then the second derivative, that'll be a point, will be the derivative of this, which is f of x, derivative of f of x, which is the slope. So we're looking for where the slope equals 0, and there's a sign change. Well, slope equals 0, look, they told us that there's horizontal tangent lines there. Slope equals 0 here and here. And those are also sign changes, right? It goes from positive slope to negative slope to positive slope. Still at 2 and 5. That was pretty easy. Next one. In the xy plane, the line x plus y equals k, where k is a constant, is a tangent to the graph y equals x squared plus 3x plus 1. What's the value of k? This is a surprisingly tricky one. The best way to think about this one is this. This is the line x plus y equals k is a tangent to the graph. So this is like the equation of a tangent line. So let me write it. So let's write it like that. Solve for y. Y equals negative x plus k. So this is the equation of a tangent line. From an equation of a tangent line, how do you get the slope? Which is negative 1. Well, that's the derivative at x1. So if I take a derivative of this guy, which would be 2x plus 3. When I plug my x value in, the proper x value in, it should give me a slope of negative 1, because this is the equation of a tangent line. So let's figure out where the x value is. So this is equal to this slope. So it's at 2x plus 3 equal to negative 1. Minus 3 minus 3. 2x equals negative 4. Divided by 2. X equals negative 2. So when x is negative 2, this is the equation of the tangent line. So I have x, I need to find my y. So how do I find it? I can't plug into here because the only thing I have here is x. I don't have the k value yet. You gotta plug it back into this equation because that has an x and a y. Like you only have two variables there, and you have one of them. So you plug it back in there to find your y. So y is going to equal negative 2 squared plus 3 times negative 2 plus 1. So 4 plus negative 6 plus 1. So I get negative 1. So y equals negative 1. So I have a point here now. I have an x point of negative 2. I have a y point of negative 1. And I can go back into this equation to figure out what k is. So that's just x plus y equals k. So negative 3 equals k. And that is a. So again, that was surprisingly kind of tricky. That's probably one of the hardest ones we've done so far. So I'm going back and forth. What are all the horizontal asymptotes of the graph in the xy plane? It's another tricky one. So there's two ways to think of horizontal asymptotes, right? There's the same thing as limits at infinity. But the reason I say all of them, because there could be a limit at negative infinity, at positive infinity, and a limit at negative infinity. Limit at positive infinity is the one we're talking about before, the very first problem, where you want to look at powers top over bottom. In this case, you really just got these two guys. So here I'm going to get 2x over negative 2x. When you plug in infinity, you get, these just cancel out, you get negative 1. So you get that. But how about if I plug in negative infinity? Negative infinity, the rule doesn't work anymore. A negative infinity, I didn't draw a negative infinity, there we go. You want to graph it. Think about the graph. So anytime you have limit x towards negative infinity, it's easier to think about the graph. You can't use the shortcuts that we do for positive infinity. So how does 2x look like on the graph? It's like an exponential graph. It looks like this. As you go to infinity, you get infinity. As you go to negative infinity, you get 0. So if I plug this in, as I go to negative infinity, this actually just turns into this. 5 plus 0 over 1 minus 0. So again, as you go to negative infinity, 2x goes to 0. It's like an exponential graph. It's an exponential graph. So you just get 5. So those are my horizontal asymptotes. I have the one you go to infinity. Look at the powers, top and bottom. In this case, they're both the same, so it's a ratio. So negative 1. And then as you go negative, you look at the graph. These guys go to 0 because it's an exponential graph. So you get 5 over 1. So negative 1 and 5 are my answers. So E. 20. Let f be a function with a second derivative given by this. What are the x coordinates of the point of inflection? So here's the second derivative. Remember, we find points of inflection. We've been asked this a couple of times. This practice test already. Points of inflection when the second derivative equals 0 or undefined, plus a sign change. So here's the good news and here's some bad news. The good news is if you know how to graph this from like Algebra 2 pre-calc, this is one of the easier problems we have. If you don't have a graph, that's going to be a little annoying. So if you try to have a graph this, or any polynomial function, your zeros here, you set your zeros, which are going to be at 0, 3, and 6. So you have 0 at 0, 1 at 3, and 1 at 6. So those are your zeros, or your possible inflection points. Now, the other thing I remember though is multiplicity. These are multiplicity of 1. So they're treated like a linear graph, like you go through them, like they're linear. And this is the multiplicity of 2. So it's treated like a parabola. It's going to bounce off of that guy. So it's positive, we start on the top right, and then we just go through the 6 because it has a multiplicity of 1. We go through the 3 because it has a multiplicity of 1. And we bounce off the 0 because of the multiplicity of 2. Because it's an even multiplicity. So you get a graph that looks like this. How does that help me? Well, remember, it's second derivative equals 0, or a sign change. So it equals 0 at these 3 spots. There's only a sign change at here and here. So my answers are 3 and 6. There we go. Now, obviously, you don't know how to graph it. Same idea, you just do a number, you just do a sign chart. You have 0, you have 3, you have 6. This is your second derivative sign chart. So you pick test points in between, plug them into the second derivative. Now, all you care about is positive, negative, and you should get positive, negative, positive, positive. So again, only a sign change here and a sign change here. So 3 and 6 would be your answers. So if you know how to graph basic polynomials, super easy problem. If you don't, it's a little more. It's still easy, but it's a little more work. Next one, a particle moves along a straight line. The graph of the particle's position, xt, at time shown above from 0 to 6. So this is position, very important to keep note. The graph has horizontal tangents at 1 and 5. At a point of inflection at t equals 2. For what values of t is the velocity of the particle increasing? So it's a little tricky. They want to know when the velocity is increasing. Remember I always talk about what does the increasing mean? Increasing means the derivative is positive. That's what it means. But it's the derivative what you're talking about. So we're talking about the derivative of velocity. So that's what this is saying. It's when is the value of velocity increasing? So when is the derivative of velocity positive? What's the derivative of velocity? XL. So I want to know what the acceleration is positive. Now, if you remember when we're talking about a graph like this, it's displacement, velocity, acceleration, original function, derivative, second derivative. So in this case, since we start with position, it would be a lot different if we started with velocity. It would be a totally different problem. But this is our derivative function. So I'm looking at the second derivative, which tells me concavity. And so I'm looking for its increase, I'm looking for its positive. So I'm looking for a concave up. Where does this graph concave up at? From 0 to 2. So it's A. Right? Again, kind of tricky. It all depends on what graph they give you. If they give me an acceleration graph, it'll just be where it's positive, 3 to 6. If they originally give me the velocity graph, then I'll be looking at the slope, because that's how you get to velocity. But since they gave me the position function, and I'm looking about acceleration, so I'm looking at the second derivative, which tells me concavity. So I'm looking for where it's concave up. Remember, this is an inflection point, so it's only concave up from here to here. But remember, even getting to that point, it's not asking about velocity, it's asking about when's velocity increasing. So that's a derivative velocity. So when's the derivative velocity positive? So that's how you get derivative 2. Let's go to the next one. 22. A rumor spreads among a population of n people at a rate proportionally to the product of the number of people who have heard the rumor, and the number of people who have not heard the rumor. That's a little annoying. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model the situation with respect to time? Where K is a positive constant. Okay, let's start from the beginning. The rumor spreads around a population of n people. So kind of n's like my total. There's n people. At a rate proportional, so it's a rate, so it means a derivative. If you notice all these sides here, they're all derivatives. Proportionate to the number of people who have heard the rumor. So we're going to do dp over dt. That part's not even scary, they all have that. So let's go back to this part, right? So at a rate proportional to the product of the number of people who have heard the rumor and have not heard the rumor. So I guess if P denotes the number of people who have heard the rumor, so P heard the rumor. So it's proportional to the product of people hearing the rumor and not hearing the rumor. Well, if people heard the rumor, how many people didn't hear the rumor? The total amount of people minus the people that heard it. It's like this. And then there's one last thing. You need a proportionality constant, which is k. If you notice, they all have a k, so you put a k there. And you get that, right? The rate is proportional, k, to the product of people that have heard the rumor, p, to the people that have not heard the rumor, n minus p. And that's the answer. Like, it sounds super easy, but it's a little confusing when you first read it. Like, it turns out to be kind of easy, but when you first read it, it's confusing. 23. Which of the following solutions to the differential equation with the initial condition y3 equals -2? So this is a separable differential equation, right? So I got to find a particular solution. So remember, the first step is to separate these guys. So I'm going to cross multiply. I'm going to get y dy equals x squared dx. And in multiple choice, it's usually not the super hardest separable differential equations. Compared to like a free response, it'll be a lot uglier. In this case, I was able to just do this. Let me just integrate both sides. So after you separate, you want to integrate both sides. And I get y squared over 2 equals, add 1 power divided by new power, x cubed over 3 plus c. And remember, next step is to find your c. That's what the initial point here, condition here is for. Here's your x and your y. So plug in 3 and equals -2. So -2 squared is 4 over 2 equals 3 cubed is 27 over 3 plus c. So I get 2 equals 9 plus c. So c equals -7. So now you want to rewrite it, right? Y equals, where am I at? Sorry. Y squared over 2, plug it back in, equals x cubed over 3 minus 7. And you're like, not done yet. You gotta get y by itself. Now, just looking at it, I know it's not a and b. It's one of these guys down here. So let's get y by itself. First step, get rid of that 2. Multiply everything by 2. So I get y squared equals 2x cubed over 3 minus 14. Then we square root it. Y equals plus or minus square root of 2x cubed minus 3 minus 14. Now I gotta decide if it's plus or minus, because it's really just between d and e. Now look what happens. If I plug in 3, I should get a negative answer. Well, then it has to be the negative one, right? I can't have it be a positive square root, because I need to get a -2. So it's the negative one. It's e. Alright, so the only way, if I plug in 3, the only way to get a negative from this is by having it be the negative answer, the negative version of it. So there we go. 24. The function of x is twice differentiable with f of 2 equals 1, f prime of 2 equals 4, f double prime of 2 equals 3. What is the value of the approximation of f of 1 using the line tangent to the graph of x equals 2? So they want a line tangent to the graph. So we got to do y minus y1 equals mx minus x1. Right. So x1, y1 is right here. 2 and 1. Remember how you find m? It's a derivative at 2. So in this case, it's 4. Like that. And then I'm going to plug in 1.9. So I get y. Let's get y by itself first before I plug anything in. So like that. Right. So again, this is it's the equation of a tangent line. That's all it's saying. We're trying to approximate. That's an equation of a tangent line. So you do y minus y1 equals m times x minus x1. Since we're doing an equation of a tangent line, just use the original function, 2 and 1. F of 2 equals 4. That's the slope. Remember how do you get the derivative? It's the slope at x1. And I don't even need this at all. I guess that tells me if it's an over or under approximation, but I don't need it. Like, it would be an over approximation. So I guess it's a check. Anyway, from here, all I got to do is plug in 1.9. So you plug in 1.9, you get 4. 1.9 minus 2 is -0.1 plus 4. -1 times 4 is -0.4. Right, 1 times 4 is 4, but then with a decimal. Plus 4 is 3.6. Why did I make it 4? It's a 1. I don't know why I made that a 4 for no reason. Right, I moved the 1 over. So that's a 1. So -0.4 plus 1 is 0.6. There we go. So that's my answer. So again, I really didn't need this at all. If they ask me, is it an over approximation or under approximation? This right here tells me the second derivative is positive, concave up, so it would be an under approximation because your tangent line would be below it. But it doesn't help me at all in this question. 25. Let f be the function defined above. Oops, I guess I need that function then. Where c and d are constants. If f is differentiable at x equals 2, what is the value of c plus d? Okay, so f is differentiable at x equals 2. It's a loaded question there. That means it's differentiable, plus it's continuous. So they're both true. So what does continuous mean? If I plug 2 into both of these, they should equal each other. So 2c, plugging 2 in right there, plus d equals plugging 2 down here. So 4 minus 2c, like that. So that's one equation. Because if it's differentiable, it has to also be continuous. Then it's differentiable. That means if I take a derivative and a plug in 2, they should equal each other. So let's do that. What's the derivative of this guy? Now remember, c and d are just constants. They're just like a number. So what's the derivative of like 2x? Just 2. So what's the derivative of cx? Just c. The derivative of this guy is 2x minus c. Right? Kind of the same idea. So this is my derivative. And again, when I plug in 2, they should be equal because it's differentiable. So when I plug in 2, they should equal each other. Just like that. If I set them equal each other, plug in 2. So I get this. Do a little math. So I get 2c equals 4 divided by 2, c equals 2. Now I know c is 2. I can put that here. But I also got to find out what d is. So go back to this other equation over here. Plug in 2 for c. So I get 4 plus d equals 4 minus 4. So 4 plus d equals 0. So d equals negative 4. Add them up. You get negative 2. So there you go. Those are some of my favorite questions, right? If I see this and it says differentiable or continuous, I know set them equal each other, plug in the number. If it's differentiable, you gotta know it's both. It's differentiable, which means when you take the derivative, you can plug in 2 and set them equal each other. And that means it's also continuous. So you just set them equal each other and plug in. When you plug in the number, you can set them equal each other. And you just gotta solve it. 26. What is the slope of the tangent line to the curve of y equals arctan of 4x at the point at which x equals 1/4? So the slope of a tangent line just means the derivative. So we're going to take a derivative of this guy at 1/4 and then plug in 1/4. That's all this is. You gotta remember the derivative of arctan. The derivative of arctan is the 1 over 1 plus x squared. But in this case, there's a 4x inside, so it's actually this. 1 over 1 plus 4x squared times the derivative of the thing you plugged in, so times 4. So I get 4 over 1 plus 16x squared. That's the derivative. And now I gotta plug in 1/4. So that's gonna be 4 over 1 plus 16 times 1/4 squared. Remember, this is all without a calculator. 4 over 1 plus, this is 1 over 16. So I get 16 times 1 over 16. That was bad. So that's just 1. So I get 4 over 1 plus 1, also known as 4 over 2, which is 2. So there we go. Not bad if you understand that slope of a line tangent, it's a slope of a tangent line, it's a derivative. Hey, look at a slope field question. Shown above is a slope field for which of the following differential equations. Okay, so remember for these, I always look for the zeros. That's my key here. So where is there a 0? It looks like when x equals negative 1, right, this whole line here is 0. So when I plug in x equals negative 1, I should get a 0. It also looks like, you can clearly see right here also, so when y equals 0, it should also be 0. So I have two ways to go about this. When x equals negative 1, I should get a 0. And when y equals 0, I should get a 0. So which one of these fills out that thing? This works for 0, does not work for negative 1. If I plug in negative 1, I would not get a 0 here. With these, I like to factor it out first. So you can factor out an x. Like this one, let's factor out the y. I can factor out y on both of them. Here I can factor out an x. And here's just what it is. Now, again, when I plug in negative 1, I want to get a 0. That's not this one. I plug in negative 1, I get negative 2 times y. So it's not this one. If I plug in negative 1 here, I do get a 0. So this one might be it. If I plug in negative 1 here, it's over there. It doesn't affect the y. Not necessarily 0. If I plug in negative 1 here, I do get a 0. So it might be that one. So how do I check now? Go to the next thing. When y equals 0, I should get a 0. This doesn't have a y at all. So it's not going to affect it. When I plug a 0 here, it does make it 0. So this is the right answer. It fits both criteria, right? It has to be negative when x equals negative 1. It has to be 0 when x equals negative 1. It has to be 0 when y equals 0. If you didn't notice the y equals 0, 1, you just have to pick a different point. Like if I plug in 1, 1, are they both positive? Actually, that would be good. They would both be positive on that one. If I plug in, pick another point, like -2. Who knows? But that's the general idea. Next one. Let f be a differentiable function such that f of 3 equals 15, f of 6 equals 3, f prime of 3 equals -8, and f prime of 6 equals -2. The function g is differentiable, and g of x equals f inverse. Keep in mind it's an inverse function, right? That's not a derivative. It's to -1, not a prime, which is the value of g prime of 3. So this is the inverse function problem. I love these. You just got to remember the formula. Inverse derivative is this. It's 1 over f prime of f inverse of x. That's the inverse formula, the derivative of the inverse. It's 1 over the derivative of the inverse. So let's plug in 3. When I plug in 3 here, so like, right, because I'm taking a derivative, take a derivative of this, take a derivative of that, you get this. So plug in 3. So we have this. 1 over f prime, f inverse of 3. So first step, we got to figure out what that is. What's f inverse of 3? So remember, that's when the y equals 3, because we're doing the inverse. So that's our y, normally it's an x. So when does y equal 3? Right here. So when y equals 3, my x is 6. So this should just be 6. So now it's 1 over 1 of f prime of 6. F prime of 6 is -2. So 1 over -2. So A. There we go. And that's it for the non-calculator portion.